Welcome to Lesson 12F, Vorticity in the Blasius boundary layer. In this short lesson, we'll continue our discussion of the Blasius flat plate boundary layer. Namely, I want to examine vorticity and discuss how to normalize it. Here's a quick review of equations and boundary conditions and solution that we had from the previous lesson. We have these similarity variables, where c is an arbitrary constant, and our ordinary differential equation in similarity form reduced to this with these boundary conditions. I pointed out previously that even though this looks like a simple equation, there's no analytic solution. So we solved it with Runge-Kutta by splitting this third-order ODE into three first-order ODEs, as shown here, with these boundary conditions in terms of the Runge-Kutta variables, capital Y. And I solved this using MATLAB. Here's a plot of the results. This blue curve is proportional to u, the x-component of velocity. And since y1 is the derivative of y2, this red curve is proportional to del u del y. In terms of vorticity, the z component is del v del x minus del u del y. But since v is very small compared to u, and changes in x are very small compared to changes in y, this term is negligible. So omega z is approximately minus del u del y. Thus we can claim that this curve is proportional to negative omega z. Note that near the wall, the slope of u is constant. In other words, the profile is linear near the wall and then veers up like this. And that is also seen here, where omega z, which is proportional to the slope, is approximately constant near the wall. And we see that clearly here, starting at this wall value. The magnitude of vorticity decays to 0 at infinity. Again, sketching our velocity profile, the rotation rate, or the vorticity, is negative since we have clockwise rotation, and rotation is defined as positive counterclockwise. So when we plot the z component of vorticity, it's negative everywhere and asymptotes to 0 at infinity. What about production of vorticity? Recall from a previous lesson our analogy between vorticity production and heat transfer. Our conclusion is that vorticity is produced only at a wall where there is a streamwise pressure gradient. But we have a problem because for our flat plate, del p del x is 0 when we're analyzing this Blasius boundary layer. So we have no pressure gradient. That implies that there's no vorticity production. In terms of our vorticity profile, there's no vorticity gradient at the wall. In other words, this slope is initially 0. And in our analogy with heat transfer, this wall is like an insulated wall for temperature. When there's no heat transfer, there's no gradient of temperature. Here, when there's no vorticity gradient, there's no production of vorticity. So either way you look at it, we don't have a mechanism for vorticity production in the Blasius flat plate boundary layer. Yet there is vorticity in the flow. So I ask, from where does the vorticity come?
Sir, I recall from a previous lesson that there is a singularity at the origin and all the vorticity is produced there.
That's right, Sean. It turns out that all the vorticity is produced right at the leading edge. If we magnify this, we can imagine some thickness of the plate and a pressure gradient in this region. But theoretically, for an infinitesimally thin plate, we have a spike of negative vorticity of infinite magnitude and a singularity at the origin. In other words, all the vorticity is produced at the leading edge singularity. Once we move away from the origin, or the leading edge, no vorticity is produced anywhere else down the plate. What happens to this vorticity? It then diffuses downstream. Let's carefully sketch both the velocity profiles and the vorticity profiles for our Blasius boundary layer. I'll greatly exaggerate vertical distance y, and we know that we have a similarity solution, so the velocity profile looks the same at any x location. It's just stretched vertically, asymptoting to capital U above the boundary layer. These are our velocity profiles. Now consider the vorticity profiles. Again, with the greatly exaggerated thickness of the boundary layer, the vorticity is infinitely negative at the singularity point. I'll draw some axes here on the velocity profiles, and similarly we'll plot omega z profiles. This one will look something like this, And as we go downstream, it not only stretches, but decreases in magnitude at the wall as vorticity diffuses into the flow. As we go farther downstream, the magnitude of vorticity at the wall decreases more, and it spreads vertically. This is all due to diffusion. And I emphasize that all the production of vorticity occurs right at this singularity point. There is no production of vorticity anywhere else along the plate. Finally, let's briefly discuss how to normalize the vorticity. In other words, our goal is to write omega z in similarity variables and generate a normalized vorticity, which we call omega z star. We start with our equation for omega z, which is negative del u del y. But del u del y was equal to u f double prime 1 over delta c in our similarity variables. So omega z is approximately minus u over delta c f double prime. But we know that delta c is the square root of 2c nu x over capital U. So omega z is approximately negative u to the 3/2 over square root of 2c nu x f double prime, noting that f is a function of eta, or similarity variables. Recall that c is arbitrary, but we picked c equal 1/2 in our Runge-Kutta solution. So for c equal 1/2, omega z is approximately negative u to the 3/2 over square root of nu x f double prime. We'll let normalized omega z, which we call omega z star, then equal omega z square root of nu x over u square root of u, since omega z star is negative f double prime of eta is negative y1 in our Runge-Kutta solution. But recall that Rex is u x over nu, which is why I separated the u to the 3/2 into these two parts. Now we see a Reynolds number here. So finally, our normalized vorticity component is the physical vorticity times x over u square root of Rex. We can use this normalized form of vorticity to plot the actual vorticity component at any x location.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.